Have you ever stopped to wonder how your phone can stream music, download emails, and let you scroll through social media all at the exact same time without even skipping a beat? I mean, it all feels so seamless, right? But underneath that smooth surface, there's this incredibly powerful principle at work. So today, we're going to pull back the curtain on that invisible engine, concurrency. Okay, let's just dive right in with a pretty dramatic statement from C++ expert Herb Sutter. The free lunch is over. What does that even mean? Well, for decades, software developers had this amazing deal. They could write a program, wait a year or two, and boom, it would run twice as fast on new computers. For free! No extra work needed. But then, that whole era came to a sudden, grinding halt. And this chart right here, this shows you exactly why that free lunch ended. For years, Moore's Law meant we just kept getting faster and faster processors. You can see that steady climb, right up until about 2002, and then wham! Engineers hit a hard physical wall. The chips were just getting too hot. I mean, they were pushing the laws of physics, and if they went any faster, the chips risked literally melting. And just like that, the free ride of automatic speed boosts was over.
So if we can't make one thing go faster, what's the solution? Well, you have to do more things at once. This forced a huge fundamental shift in computing, a whole new way of thinking that we can picture as the octopus orchestra.
And this brings us to the core idea itself. Concurrency. It's the ability for a system to deal with more than one task at the same time. Now listen closely to that phrase, deal with. It's really, really important. It's all about managing and making progress on many different things in overlapping periods of time, which, as you'll see, isn't quite the same as doing them all at the exact same instant. This is where that whole octopus orchestra idea really brings it to life. Just picture it, an octopus. Each one of its tentacles is playing a different instrument. One's on the drums, another's on the violin, maybe another on the piano. They're all working together in perfect harmony to create one single beautiful piece of music. That, in a nutshell, is what a concurrent system looks like.
And that idea of an octopus juggling all those instruments brings us to a super important distinction. Because, there's a big difference between dealing with a lot of things and actually doing a lot of things. So let's clear up that confusion right now.
This classic quote from Rob Pike, one of the minds behind the Go programming language, just absolutely nails it. Concurrency is about dealing with lots of things at once. It's about how you structure your work. Parallelism, on the other hand, is about doing lots of things at once. It's about the actual execution, running multiple tasks at the exact same time. Probably the best way to get this is with a kitchen analogy. So on the left, you've got concurrency. Think of one really busy cook, juggling multiple orders. They chop some salad, then they quickly turn to stir the soup on the stove, then they go back to chopping. See, they're dealing with both tasks, but only actively doing one at any given instant. But over on the right, we've got parallelism. Now there are two cooks, or you could say two processor cores. One is totally focused on chopping the salad while the other is stirring the soup. They are literally doing two things at the exact same time. Okay, so we get what concurrency is now. But how do our computers actually, make it happen? Well, the operating system gives us two fundamental building blocks to work with, and you can think of them as construction crews and team workers. First up, we have the process. A process is really simple. It's just a running program. Your web browser, that's one process. Your music app, that's another. Think of each one as a big, heavyweight, independent unit. It's got its own private memory, its own resources, and it's completely isolated and protected from everything else running on your computer. And then we have a thread. Threads are much, much smaller. They're like little lightweight workers that live inside of a process. So a single process, like your web browser, can have dozens of these threads running at once. One thread might be handling your mouse clicks, another one's drawing the web page, and a third one is playing that video in the corner. And here's the crucial part. All of these threads, inside the same process, share all the same resources. The construction analogy really makes the difference clear. So processes are like separate, independent construction crews. Each crew gets its own construction site, its own set of tools, its own blueprint. This is incredibly safe, right? If one crew completely messes up, it doesn't affect any of the others. But the downside is that setting up a whole new crew is really slow and expensive. Threads, on the other hand, are like individual workers on the same crew. They all share the same tools and the same blueprint. This is way faster and more efficient, but now they have to coordinate very carefully so they don't get in each other's way. So once you have all these different crews and workers running around, a brand new challenge pops up. How in the world do they talk to each other to actually get the job done? For this exact problem, the operating system provides an official toolkit, and it's called Inter-Process Communication, or IPC for short. You can just think of it as the set of rules and mechanisms that allows all these different concurrent tasks to safely coordinate their work without stepping on each other's toes.
And this communication really happens in two main ways. First, there's shared memory. Think of this like a communal fridge in an office. Anybody can put data in and anybody can take data out. It's incredibly fast. The other way is message passing. This is more like sending a rubber duck down a pipe from one person to another. It's a direct message through a dedicated channel. It might be a little bit slower, but it's way more organized and really helps avoid conflicts.
All right, so we've covered processes, threads, and how they talk to each other. But let's bring this all back home. Why does any of this techie stuff actually matter? Well, it's because you live, work, and play in a completely concurrent world. Just think about it. That app on your phone that never, ever freezes, even when it's syncing data in the background, that's concurrency. A web page that loads all its text instantly while the images are still popping in one by one? Yep, concurrency again. Streaming a 4K movie without it constantly stopping to buffer? You guessed it. In fact, the entire cloud, with millions of computers all working together, is basically the ultimate octopus orchestra. When you get right down to it, concurrency isn't just some clever trick for engineers. It's a fundamental shift in how we build software to better reflect reality itself. I mean, our world is complex, it's overlapping, and it's simultaneous. Things don't just happen one at a time in a neat little line. So the real question is, why should our programs be any different?